hearing impaired, so we're testing out some ways of maybe miking up and whether they can hear me better in the back of the class. So that's what we're doing. Okay. I'm not sure why we're doing this. Maybe Joe is selling them later. I get a commission on this. Okay, folks, so what we spent our time on Thursday doing was looking at a tower. We looked at a force there, and we calculated the components of force in the direction of that tower. Now, what we're going to do is we're going to continue that, and what we're going to be able to see then is how we can solve an equilibrium problem now. We're going to solve for those unknown tensions. So we've been given tension in one of those things. We're going to find a way of using our equilibrium equations, basically, to solve for the unknowns. And just like we did in 2D, we want that resultant to be equal to 0. Those sums of those forces, if that particle is truly statically set and in equilibrium, see, I can talk out here and people can hear me. It has to be equal to 0. So when we recall our resultant in 3D, we just have that extra k vector there. But the key thing is that has to be equal to 0. And how does that equal 0? Each of those components has to be equal to 0. But the nice thing is that's just a bunch of scalar equations. We can do that. Very simple. Now, we'll go ahead and look at your first handout there, the one with the tower. It's the same tower. What we did, we kind of cheated and talked about how to calculate that force that we're going to need for this equilibrium problem in the last lecture. Remember, that was that two-point method, so we walked through that approach in terms of calculating x2 minus x1. Sorry for the quality of that. Let's see. But again, our free body diagram is going to consist of the body itself is just that point, point A. What we do now after that is start putting on the forces, the known forces and the unknown forces. AC was a known force. We went through the last lecture and calculated those components. Unknown forces are going to be AB, AD, and P. So we've got three unknowns. We've got three equations of equilibrium there. And then the other key thing you need to do with your free body diagram is be putting in these dimensions. In our particular case, our dimensions are going to be a series of points that we're going to use that third method for calculating angles and that sort of thing. So that's what your free body diagram, and your handout already has that. What we're going to do is then construct these equations and see how we can go about solving for these unknowns. I think we're going to have to get an extra sturdy one here. So it's not even going to cooperate. So we've already solved for the components of AC. What we need to do is break now AB, and AD into their component forms. Now they will contain an unknown, but we still need to get it into those X, Y, and Z components so we can construct those scalar equations. Okay, so when we consider, and you'll have to, I don't have my picture up here anymore, but when we consider the X components of AB, we start and look at B, we note that in terms of x, it's 40 back. So we start off with a minus 40. And then at A, it's going to be equal to 0. So my dx component of that is going to be minus 40. We comfortable with that? We're paying attention to signs.
30 on here. This says 30.
Does it say 30? Oh, that's the z component. You're right. Yeah. Okay.
Which one are we doing? A or the one you gave us today?
We're doing the one today. What we're looking at now is AB, cable AB there.
But these diagrams were...
No. Z.
The Z is 30. There's no 40 in the direction.
Oh, God. All right, let's let's start off. dx starts off at a minus 45, right? Thank you. And that's in feet. Okay, everybody's awake. That was a test to see if you guys were awake or asleep. Okay, now dy, well, that's the easy one. 0 minus 90, we already did that one. And then dz will be 30 feet in the positive sense, minus 0 or 30 feet. So we can express now our cable AB like so. So we just simply express that as in terms of a vector. And that describes the cable itself. If you start at A and you want to work yourself to B, that's the steps you'd have to take to get there. Now, we can also calculate the length. Like so, just simply Pythagorean theorem. And then where we're going with this is we want the unit vector. Because what we're looking for is the components of force. We don't care so much about the cable. The cable we're using in terms of getting ourselves the directions of this force. And basically, it's just taking this vector and dividing all of those terms by 105. And what we'll get then, and adding an extra digit there for precision and stuff, I'll carry 4 digits there, is we basically now have our unit vector in the direction from A to B. So unit vector, all of those terms squared basically and summed up will be equal to 1, which is the definition of our unit vector. And the key thing now is then I can define my force direction by just simply multiplying it times the magnitude of that force. Now, the problem is I don't have the magnitude for the force. That's an unknown, but that's fine because That's only one unknown. I've got it broken up into components, but it's still just one unknown now. Now, what we're going to do is the same thing with AD, and instead of walking through that, we'll just I'll put up a couple of key pieces there. You can construct the rest at home, but it'll be pretty obvious when you look at it. Boring you already, am I? But same steps. We'll skip some of the steps in between there, but basically we end up with our vector by going through the steps here of subtracting D from A, the components of D from A, divide through by the length of it. We created that by doing the Pythagorean theorem. And basically, again, we have now one unknown, but it's expressed now in terms of its component directions, x, y, and z. The final one then will be the unknown is P. And that one, basically, we don't even have to worry about calculating because it's acting in the positive y direction there. It's acting in that positive y. Unit vector is going to be 1, so we don't necessarily have to walk through all these steps. Okay, so the key thing now is we've taken these unknowns and we've defined them now into these scalar components, x, y, and z. Why we do that then is basically now we're going to do those scalar equations. We're going to set Rx equal to 0, Ry equal to 0, Rz equal to 0. And that's something then we can do on a calculator or a matrix solver. Okay, I'm not making you electrical engineers. Equilibrium equations. Okay, sum of the forces x equal to 0. And again, I'll choose my positive direction, and according to my picture, it's kind of off at that weird angle there. And then I'll just look at these various components. So AB, so that's the component from AB. AD, P, there's nothing there, and then finally AC. And then that whole equation equal to 0. So all I've done is just simply taken all of those forces with known forces, which happens to be the AC, and then my two unknown forces. P doesn't contribute to that because it only has a component in the y direction there. And that's what equation 1 looks like. Again, I'll do the same set of equations. I'm going to go grab all the y components of these things. Oops. And when I get done with that one, I'm just simply grabbing all the components of the y direction there. The one thing that we have in there that's different now is we got p in there. And then simply grab those components. Now again, note that we have three unknowns, FAD, FAB, and P, and we have three equations. So your choice of solving it, if you have a matrix solver, you want to solve and plug it in, set up a matrix, that's fine. Substitution is probably the easiest. So in substitution, what we want to do is I take equation 1 and I'm just simply going to solve it for FAB. And then I'm going to substitute that in somewhere. So FAB, if I go through, divide through by 0.4246, hot in here, isn't it? Okay, so I just simply took this equation, divided through, and set FAB on it. I basically brought those two over to the other side of the zero there. Comfortable with that? Okay, now all I'm going to do is substitute that into 3 now. Note that I've got equation 3 here that's in terms of FAB and FAD. I just solved for FAD or FAB there. So I just rearranged the equation a little bit. I brought the 520 over there. And all I did was just simply, in this part here, substituted in what I just solved for that. Notice now it's down to one equation, one unknown in that equation. Oops. And I end up with 1602.59. Now, in terms of if I was going to report that, I'd simply cut it down to 3 or 4 digits there. I do carry that extra digit around, though, because what I'm going to do now is take that and substitute it back into this equation. So back to my new 1 there. Now again, why I'm carrying those extra digits is that I have an interior calculation here. I'm going to carry those extra digits. Again, I report it as 1240, but in terms of carrying around extra calculations and stuff, I want to carry those extra digits to keep my precision. And then finally we go to 2, and then we're just simply going to substitute the FAB and the FAD in there and solve for P. So my one unknown there is just simply going to be the P. And solve for that, and since I'm not going to substitute that anywhere else, basically I just keep it down to my 4 digits. So that's really all there is to equilibrium in 3D for particles. Just an extension of what we did in 2D. We just have an extra equation there. But the key thing is then we're going to have to spend the time and break things into these components so we can add them and come up with these separate equations here then. And then we just play around with substitution or matrix methods, whatever you're comfortable with. Okay, you ready to solve 3D? You what? Okay, now we get into the fun stuff. So equilibrium, the nice thing about it is you've already got yourself a tool. You've got an ability to solve for particle equilibrium, which is part of it. We're going to go into rigid bodies here next. But it's a tool, basically, in terms of being able to solve for unknowns. And as engineers, you'll be using that for the rest of your life. I'm going to have to work on improving this. Just, yeah, I think I'll do that. Okay, well, I'm getting myself together here again. What we're going to be doing in Chapter 3 is understanding this concept of rigid bodies, understanding the assumptions involved in it and what we can do with it. And then we're going to get into this thing called moments, 3D and 2D moments. We'll be doing moment calculations. And then a special kind of moment called a couple we'll be playing around with, and then calculating equivalent force systems. So this is where the real meat of statics is going to be coming in here. Understanding this particular stuff is basically going to give you the tools to be able to go out and solve a lot of things. Do this without launching my... Okay. So what we're going to be doing with rigid bodies, we're going to be looking at something more than a point. We're not talking about going to the gym or anything like that. Now, when we talk about loads, when we talk about real materials, the point of application of a load is important. So if I were to put my load here again, what I'm going to see when I look at that material, and I'm looking, say, for example, on the insides and so, I'm going to see some sort of a deformation like so. And if the load's over here, well, then the deformation might look like that. I might be pulling instead of pushing. So I might be indenting it here. I might be pulling it out here. So in terms of real materials, and when you get into mechanics of materials, this is what you're going to be starting to look at. What's going on the inside of that particular material? In statics, what we're going to do is make an assumption concerning what we call a rigid body assumption. But then that gives us the ability to go in and solve some things rather quickly. So RB will be my shorthand for rigid body. We'll put that up here too. Okay, so the assumption we're going to make with this is that the other shorthand there is WRT with respect to. So what we're going to assume then is that the deformations are small compared to the size of the body. So if the body is a big truss or it might be a building or something like that, and our deformation is down to a half an inch or something like that, then the deformation we can consider small in terms of the size of the body. The other point is what we're really interested in statics is the external forces, external to that rigid body. Now, with that, we get to learn yet another cool word. In Beer 3.3, there's this thing called principle of transmissibility. So again, another word you can impress your English major friends with. What that means is we're going to be able to take advantage of this assumption of a rigid body and say something about these external forces. Okay, so what we're saying then, or what the principle of transmissibility says, is that the external forces, and again, we were talking about what we're interested in terms of this studying a rigid body, is what's going on externally there, are independent of the point of application of this force. So we'll consider a rigid body here, and I always laugh that we engineers like the engineering baked potato. We always have this baked potato-like thing. And what we're going to do is consider a force acting on that body. And it'll be acting along a line of action there. Highlight that point. And because of that force, we've got this body setting on some springs here. Can you see? Am I blocking you too much here? What we're going to be able to do is measure some sort of spring forces caused by that force. No, it's LOA, line of action. Keep asking those questions as you'll figure out my shorthand here. So what that's saying then, that's an equivalent to the same body, the same set of springs. Doesn't look the same, but take my word for it. Same line of action, but I can put the force over here instead. And what principle transmissibility says then is that my spring forces over here are the same as the spring forces over there, but with this force maybe not even on the body. It may be off the body somewhere. Now we'll see why that's nice is then if we can move that force along that line of action there may be an easier place to do some of these calculations that we'll get to see when we start doing moments and that sort of thing. If there's an easier place to put it, then we want to put it there. We don't necessarily want to spend a whole lot of time trying to figure it out if it happens to be located in the one position there. Okay, so now we're going to look at this concept of what we call moment of force. We shorten it to moment. Question?
You move the force off of the body itself?
Yeah. What we're saying is that if I can assume that this thing is a rigid body, then I can slide my force over here and be able to calculate spring, the forces in the spring that's holding it in place would be the same as this one here. But maybe it's easier if I slide it over here or slide it over there and that sort of thing. It's just a concept that says we have an ability to move it to a place that's easy to calculate. That's where we're going with that. Any other questions on that?
Force is pulling it, right? On the right side?
It's causing the body to go this way. Let's talk about this real quick and then let's go back to that question. Because I think this will answer it. So we'll consider what a force does to a body. What that force is doing is that one of the aspects of having that force on there is that it's going to want to move the body to this new position, right? It's going to follow along that line of action. So it doesn't matter whether it's here, whether it's there. What the body wants to do as a result of that force, and it's rigid, so it's not squishing or anything like that, it's just simply going to be charging along that line. The other thing when I consider, I'm going to draw this high so the folks in the back can see it too. Go back to our body. And we'll consider some point here on the body that happens to be on the body, but it doesn't happen to be on the line of action of this force. So think about it. If I took that body and there was a force down here going in this direction here, it's going to want to push me along my line of action here. But if I held it at that point, it's also going to want to twist me about that point. So what we're going to see then is if I held it about this point, allow that force to act on it, the tendency for the body now is to also rotate about that point because it's not on the line of action. If it's on the line of action, if my point is along that line of action, the only thing my body will respond to is a force moving along that line of action there. If I take a look at a point other than something along the line of action, it's going to want to do that and rotate me. This tendency to rotate then is what we call the moment of force. And you're probably familiar with it when you think about it in terms of if you do any car repairs or anything like that, torque. We tend to describe moment in terms of torque. Now, one thing I'm sure you've all read, because you're keeping up with all of this, is that moment is a vector. And we'll see that as we kind of describe how it works here. It's a long one. Okay, so the magnitude of a moment vector is going to be the force magnitude, which is a scalar, times the perpendicular distance to the line of action. There's my colors. Okay, so I've got some point, and I've got some line of action here, and then a force out here acting along that line of action. What that's telling me then is then the magnitude is going to be just simply that magnitude of the force times the magnitude of that perpendicular distance to the line of action. This is the point that catches a lot of people off guard. It's perpendicular, and we'll see why. Units. When we express a moment, it'll be in force times distance. So examples. Kilogram, meters, foot, pounds, that sort of thing. So again, remember when I was telling you to carry those units around in your calculations, because if you're calculating a moment and something comes out in kilonewtons times kilograms or something like that, then you know you're kind of not in the right spot there. You want to see it in terms of a force and a distance. That's how we express our moments. Because it is a vector, the direction is perpendicular to the plane created by the distance to that line of action and the force itself. In this particular case, in 2D, it'll be in and out of the board. A good way to remember it is think about it in terms of the axis of rotation. If I have this force here, and it's on the plane, when it rotates, it's going to rotate about an axis that's perpendicular to that. So a good way of thinking it, especially when we go to 3D, because then that's going to be all over the place. But in 2D, it's going to be basically in and out of the board, because the plane of the D and F are basically the plane of the board. So again, think of it in terms of just if it were to rotate, what would that axis be? That describes that moment vector. So it's a little weird in terms of forces. And then finally, what we consider is the right-hand rule. So take your right hand. Your fingers have a natural curl to them. Think about playing piano. You're always supposed to keep them curved and that sort of thing. That's the rotation. Think about the rotation there. Your thumb is pointing in the positive sense according to the right-hand rule. So it's very cool. You can always tell civil engineers when they're in the EIT exams because everybody's doing this sort of thing. The right-hand rule, basically, in terms of our 2D, counterclockwise is considered positive. So it's rotating in the counterclockwise. My thumb is pointing out of the board. So that's considered a positive rotation via the right-hand rule. And then obviously the other way, if it's twisting in a clockwise fashion, your thumb's pointing into the board. So it's pointing into the board, or we consider it negative. And basically, this is how we're going to keep track of it in terms of signs, positive and negative. Sir?
I thought moment vectors don't exist in 2 dimensions because it's a cross product, and cross products only exist in 3 dimensions.
We're going to do a cross product in 2D just to show you that that isn't right. We can do that. We just put zeros in for Z.
You do?
Yeah. It's very simple. We're going to do that today, though. Very good thought. But yes, we use the cross product as more useful for us in 3D. And what we're going to go through in terms of that second handout that we got there is all the different ways we can look at 2D. That we like 2D because there's like 4 or 5 different ways for solving the same thing. When we get to 3D, then it gets a lot more difficult, and we do want to use that cross product. But we can use it in 2D. It's just a lot more laborious. It's like a lot of work for nothing. But good thinking, good thinking. Where am I? Oh, perfect timing. Cross product. I'll slip you that 20 later. Somebody must have read the book. He knew I was coming right up to that. So we will talk about one of the ways of solving it. Now, again, cross product is going to be a lot more useful in 3D, but still it helps us, gives us an understanding of how moment works. And the definition for that is on Beer 3.4. Golly. Sorry, it's my son. I'll tell him he sang to the whole class. He'll be very impressed and probably mortified. Okay, so let's consider a point O. And there's our line of action. Now, what we're going to say is that I'm going to draw a vector to a point A, and we're going to call it R. So we've got a point O that I'm interested in discovering or trying to find out what this moment caused by this force is, this twisting action. And I'm going to find a position vector. I'm going to define a position vector from O to A, and A is just somewhere on that line of action. So let's and we're going to be able to define it in terms of our Cartesian coordinates, like we just defined in terms of the two-point process there, except we only have, we won't worry about the k direction there. But it's just simply we can define the vector from O to A in terms of our I, j, and k, and that's what we're going to want to go with that. And as I said before, that A is just simply any point on the line of action. So it doesn't have to be, the force doesn't have to be anywhere near. It could be off here in space somewhere. But if I can define a point A that I know is acting along that line of action of that force there, then I have the ability to solve for that. And note that now that I've got R defined here on this plane of the board, I've got F defined on the plane of this board here, I've defined a plane. It's the plane of the board. But again, think about that in terms of my moment vector is going to be perpendicular to that plane. We'll see that especially when we get into 3D. Now, what cross product is simply is just the multiplication approach for vectors. One way of multiplying. There's actually two ways of doing it, but it's just simply a multiplication of vectors and what we use is a big X type there. You'll see that when you look at your math books and that sort of thing. And that's how we define it. So let's take a look at this. Moment at O is a vector, underlined, is going to be equal to this cross product of R crossed into F, which is going to be what we call this cross product. Now what we're going to do is we're going to talk about the mathematical approach, and then we're going to show you how a much easier way of doing it in terms of the Cartesian coordinates. So the mathematical approach says the magnitude is the magnitude of R times the magnitude of F times sine of theta. So what that sine of theta is, where'd my blue go? So we got an R vector like so. Theta is just simply the angle created by those two vectors. If I slid my R up to this point A here, I'd have these two sitting like so. And basically the theta is the angle between those two. Now, an interesting thing, let's think about this, and I'll switch to a green here. When we look at this, okay, if we look at that angle there, what's this angle here? Theta. Okay. Now, if I've got a length defined here as R, What's r times sine theta? Yeah, it'd be that perpendicular distance, right? You remember it defines that right triangle? Are you familiar? You're comfortable with that? So if I take r times sine of theta, I get that distance, d. Now the interesting thing is that kind of, remember our definition of a moment was the magnitude of this force times this perpendicular distance. So note that we already have that there when we consider that's simply FD, like so. So the nice thing about the cross product, and this is why we like it so much, especially in 3D, is it takes care of right angles and stuff like that. We don't have to worry about calculating that perpendicular distance. It's already defined for us. Now a couple of notes. No matter how we set this up, d is always going to be constant. So anywhere in the LOA, think about that. If I move that around, that angle is going to change with me. But basically, it's always going to define that perpendicular distance. D will remain constant. So it's making it a little bit confusing, but in the long run, it makes it easier. F can be anywhere in that line of action there also, because we just talked about that principle of transmissibility, which came from our assumption of making that rigid body assumption. Deformations are small. So that's the mathematical definition of that. But we don't necessarily, especially when we go into 3D and that sort of thing, we don't want to be going and measuring angles and stuff like that and trying to calculate that r distance. So there is an easier approach if we can get it into the x, y, and z components that we just spent all that time doing with the particle equilibrium approach there. What we'll find is that the cross product then can be expressed with rectangular coordinates in a much easier way. There's a faster way of doing that. And the way we do that is, first of all, we have to express this r vector, this position vector, as your author calls it, in terms of its various components. And we've already spent a whole bunch of time doing that with the force. So we can express both the position vector and the force vector in terms of components, paying attention to signs. Again, signs are very important. So what we're going to do is use the cross product approach in terms of solving for this using the cross product. And again, since moment is a vector itself, it can be expressed in terms of mx, my, and mz. And when we get done with it, in terms of putting this together via the Cartesian coordinate system, is that it's simply going to be a bunch of scalar equations. So mx, the mx component, the x component of the moment, is simply going to be expressed by the y component of r times the z component of f minus the z component of r times the the y component of f. Similarly, now note, this is x component. There's no x components over here. So again, in terms of thinking of that position vector, well, of course, if you're going in the x direction and the force is going in the x direction, it's not going to cause any twist about that x. So it's only going to be the components perpendicular to the x direction that's going to cause. And we'll see the same thing with y. And also the z. So again, if you're solving for y, there should not be a y component over on this side of the equation. If you're solving for z, you should not see a z component over there. That's the definition. There's a couple of different ways of remembering it. You can write these down, and again, you do have the crib sheet capability for your quizzes and exams and stuff like that, so I suggest writing that down. What was our question? Oh, sorry.
How do you know you're going to have rxfy minus ryfx and not the other way around, like ryfx minus rxfy?
Very good question. It's dependent upon this order. If it was reverse of that, then it would be f cross r. And what you would get is you would get the same, you would get the correct magnitude for the moment, but you get the opposite direction. So it's, yes. And that's a good point. I'm glad you brought that up because it is very important in terms of when you do cross product, and we're going to see this, is keeping the order, not only keeping the signs correct, but keeping the order of the equations correct. So this is basically, if we do the calculations with r cross f, they would be reversed if we did it the other way. Now, again, most people, you remember how to do a determinant? Okay. Most people remember it in terms of setting up a cross product via the determinant. And there's a couple of different ways you can solve for a determinant, but setting it up is the critical thing here. So MO, and you set up your determinant in terms of your unit vectors in the first row. Question? From here to here, it's basically how it falls out of the equation when we do it in terms of Cartesian coordinates. So it's not, yeah, you can set it up as a matrix if you want. But it's basically a defined equation. This is basically how you define a cross product in vectors. And don't worry, we get to do another multiplication method yet. Okay, so our first row is going to be a 3 by 3 determinant. Matter of fact, we'll put that up there, 3 by 3. So the first row, and again, order is important here, is our unit vectors. Our position vector, in terms of x, y, and z components. And remember, determinant doesn't have any of the little curly cues at the end there. But we'll note then if we want to walk through this, you recall how to solve this. In terms of I, we would go this way in a positive sense, right? Which, let's like there is going to be my ry times my fz. And then when I go the other way, always do that little extension of and then when we do the negative direction there, when we come back this direction there, note that it's going to be the rz times the fy. We'll pick another color. For the j, rz times fx. And then the negative will be Rx times the Fz. There is also an approach of doing it if you're familiar with it in terms of the little subdeterminants there where you take this one and then solve the little 2 by 2 there. You're familiar with that one? I'll post that on the web for those of you that want to remember how to do that. Okay. The way the determinant works, remember, is you go this way and then you go this way. You go positive this way, multiply all the terms.
Can you just cover one?
You usually cross out
That's
the
the
row
2 by 2.
column and then solve the 2 by 2.
Oh, you want to do the, okay, you want to do,
That's just the normal way.
is that what you guys are familiar with? Let's do it that way then. Okay, I solved it, I used to solve it that way, but let's do it that way. So if we're going to do I, then what we do is eliminate everything in this row and everything in this column and in this row, right? So then we have the little 2 by 2, right? So positive this way, negative cross that way, right? Got those terms there? And then the next thing we do is then we go do the j component. When we do the j component, we drop this and then this and this. So we would have a 2 by 2, which would then be Rx, Rz, Fx, Fz, right? And then positive this way. Oh, what did I do wrong here? Oh, that's because every other one is negative, right? Got to remind me of that, yeah. So when we go to that one, it's negative. Again, I'll post that. I've got a whole little sheet written up on how to do it via the subdeterminants there. So are you comfortable with that?
Yeah.
It's kind of the other way to do it, yeah. This is just if you want to walk around and impress all of your friends with your mathematical ability. In terms of what you need for this class, just write this down if you need it on your crib sheet. That's the key thing. Okay? Okay, so that's cross product. One other thing we need to talk about is one other theorem that we can use to help make this moment calculation a lot easier. And again, this is a guy who had a lot of time on his hands and came up with a great, cool theorem here, Vergnon's theorem. Okay, so let's consider, we have a point A here. And we got a bunch of forces acting at it. So various magnitudes, various directions, and that sort of thing. And we've got a point O here that we're interested in finding the moment due to those forces. Now, key thing is note that they're all going through a common point, right? So what do we call that when all the forces go through one point? That'll be on the test. Concurrent. You'll be hearing that a lot more. Okay, what Vergnon came up with is he recognized the fact that I can take F1, F2, and F3 and add them together and create a resultant, right? We did that because they're all at a point. So another way of expressing that is either the resultant or I can break it into a bunch of forces like that. But what he's saying then is then I can take that and I can break it up into individual cross products. Now, that may seem like a lot more work, but actually the nice thing about it is then I can take a single force and break it up into components and do a simple cross product on each of those two. So it just basically recognizes the fact that if all the forces go through a single point, we're just simply doing a cross product of the resultant of that. Or if you want to individually look at forces like that, we can break it up this way. Okay, we'll look at the next handout. There's some missing terms in there, but we'll talk about it. Now, what we're going to see in terms of the handout here is a variety of ways of solving the same problem. We're going to solve the same moment calculation 4 different ways. Now, I'm always asked the question, do I need to know all the ways? Well, if you want to be an engineer, yes. You need to be comfortable in terms of how to solve all of these different approaches. It's saying the same thing. You're going to be using this to correct yourself. So one way of, the nice thing about having all these multitude of ways of doing it is it gives you the ability then to check yourself. Sir? Maybe. I don't know. Yeah, I haven't decided yet. So that's why I say, people ask me, do I have to learn them all? Yeah, again, you're engineers. You're going to have to learn them all at some point in time. This may be the one method you don't do in terms of going through and calculating lines and stuff like that. But you'll find you'll be comfortable with one method than the other and stuff. But you need to know them all, basically, to be an engineer. Okay, so what we're doing in this example is we've got this plate. It's a 4x4 plate. So 4x4, there's, I guess I got it in terms of feet. And I've got a force, a 30-pound force there that's going through A and then going through the middle of the side there. So the nice thing about that is I can calculate that line of action just with my y-intercept approach there. And I find that I've got a slope of 2/3, so a rise of 2 for every 3 over, and then my y-intercept's going to be 2. Easy enough. So it's just a couple of lines there. Now, the definition of moment, again, is that magnitude of that force, which is 30 pounds, times the magnitude of the distance, the perpendicular distance to the line of action. So now I have to find that line of action. Now, how do I find a perpendicular line if I've got a formula expressed in terms of the y-intercept? What's the negative reciprocal? Thank you. So we go through and we can solve for the negative reciprocal, which is going to be 3/2. And then I can find my y-intercept by substituting in my b because I want it to go through b. I'm trying to find the moment at b, so I substitute in my b as 2 and 0, plug it in, and I find my y-intercept of 3. Simple. You've done this in high school. Now, the next thing is I need to find the distance to that. So I need to find the distance to that intercept there. So what I'm going to do is I'm going to find the intercept. So we determine the intersection by simply setting them equal to each other. The one point that they actually equal to each other is going to be that point where they intersect. And then what I'm really interested in is once I find that intersection, I'm going to basically want to calculate the y component and the x component there. So I can go through and solve for the x component there. Might as well get the other one up there then too so you can see it. So I solve for my intersection there at x equal to 6/13 and y equal to 2 times 4/13, or 2 and 4/13. Real nice numbers to deal with. Now the rest of it you actually have, so we'll just kind of put it up there. The key thing is then what I need is that perpendicular distance, that d. So I'm going to go in and calculate that via my Pythagorean theorem there, and I come up with a value of 2.77. So that's the distance from B to that intersection. Once I have that, then moment in terms of magnitude is just simply the magnitude of the force times the magnitude of that distance to the perpendicular that perpendicular distance to the intersection of the line of action there. So, and I end up with 83.2 foot-pounds. Again, making sure that I'm carrying my units around there. When I get a moment, I expect to see it in terms of force times distance. Direction into the page. Well, how do I know that? Again, think about that twist. That force is going to rotate me this way, right? If I hold it at B, that force is going to want to rotate me that way. Then I have to think about my right-hand rule. My curl of my fingers is going to indicate a rotation that way, so it's pointing into the board, sign negative if we express it in terms of algebraically. So when we get done, it's a vector, so we have to describe it in terms of magnitude, its units, and then direction. So this is one way of doing it. Okay, so that's the hard one. But that's the strict definition of it. And the reason why I wanted to put that up there was just so everything else makes some sense here. Okay, the back side of your first page there is the same problem now, but what we're going to do is approach 2 is we're going to think about this principle of transmissibility we talked about. We can slide this force somewhere. As long as it's on its line of action, I'm going to slide it all the way down to here. Now, interesting thing, I can then, once I've got it down there, I can break it into its x and y components. Now, let's think about the x component. What does the x component do in terms of twisting about B? Nothing. It goes through B, so it's not going to cause any twist. It's going to push me, sure, but it's not going to cause me to twist. Only the y component is going to cause me to twist. So in terms of my moment definition there, then, what I need is my perpendicular distance and then that y component. So what we're going to do is just break our force into components there. So we went in and did a calculation there, inverse tan of the 2/3, which was my slope in my first demonstration there. And we calculate that angle of 33.69 degrees. And then again, I'm not interested in the x component, I'm interested in the y component. So I take that 30 pounds times the sine, since it's measured from the positive x-axis there. And what I find is my force now can be, my 30-pound force has a y component of 16.64 pounds acting up. And then I think you've got the rest of it there. The magnitude then is that 16.64, but now I've got a longer distance there because my intersection now, where I slid it down to via transmissibility, is going to be 3 over. So it'll be 5 feet, it'll be 2, and then remember it's for every 2 down, it'll be 3 over. Question?
Explain again where you got that 5 foot.
Good. All right. So remember, it's 2/3 there, so for every 2 down, I go 3 over, right? There's 2 here, so I have to go 3 over. 5, and then 2 to get to B. Good question, though. I want to make sure everybody understands that. So that's why we like transmissibility, is that I can slide it to some place where I can maybe easier. There's a lot of work to find that perpendicular distance to the line of action there. If I can slide it somewhere where I can break it up into an x and y component, much easier. Everybody got that? I want to pull it. 2 more to rush through here. Okay, Bergnon. Oh, we already did that one. You're probably missing that, but okay. Bergnon says then I can do it in terms of 2 or 3 different equations. So what I'm going to do is I'm going to break my force. I'm going to leave it there, but I'm going to break it up into its x and y components. So my y component we actually solved for earlier there is going to be 64.64. The other piece we'll need then is going to be the x component, which is now going to be times the cosine of that, and will be about 25 pounds, so 24.96. Now things get a little tricky here once you get this written down, we'll okay, ready? Now the rest of it you've got, but it's a little tricky here. We have to be careful in terms of signs. Okay, and I always manage to hide what I need. Okay, so now we have to pay attention to the fact of which one's twisting which way. So again, I'm holding it at B. Let's think about what Fx is doing to me there. Fx is saying, I'm going to twist you this way, right? If I hold it at B, perpendicular-wise, it's going to want to twist me this way, which is my counter, or my clockwise, right? Or negative. Hence, I have the negative sign in front of that. So big number there, times 4, so the perpendicular distance up to where the x component of that is 4 up, so nice perpendicular distances. That's why we like the Cartesian system there. But now think about Fy. How is it going to twist B? It's going to be the opposite sense. It's going this way now, right? So we see that as a clockwise twist, and we have to pay attention to the sign there. Once we do that, though, add that again, and then it's only 1 foot over. Again, line of action is along that third line there, so it's only 1 foot over. Add them together, and what I get then is the same value that I calculated for the other two approaches. Tricky thing about Vergnon, though, is you've got to be very careful about, okay, which way is it twisting, because it will change that magnitude. If you add them up together, basically it's not going to be very useful to you. But again, it ends up with the same result. It's negative, which implies then my axis is pointing in, the vector is pointing in, and it's rotating this way. So the culmination of those two is going to be a force or a rotation in that direction there. And then finally, getting to cross product. I know you were anxious to look at that. Again, cross product's set up for 3D, but we can plug in zeros. Again, it's a little more work. You may not want to do it, but get used to it because we're going to have to do it in 3D. So, a couple of things to note here. We're going to do this calculation for the r vector. Now, what I'm going to do is I'm going to pick some easy point on the line of action. That's the nice thing about the cross product. Find an easy point. So I'm going to go to that point C there, which is at 0 and 2, and I'm going to go through my calculation to calculate that vector. So that vector says, for me to get from B to C, I'm going to have to go -2 in the x direction and 2 up in the y direction. Okay? Now, again, that's not perpendicular. That is not the perpendicular. We solved for that earlier there. But with the cross product, we don't have to worry about that. As long as we solve it in terms of the Cartesian approach here. We've got our force vector that we described earlier there. We broke it up into x and y components for Vergnon and the sliding vector approach. And then just simply plug it into our determinant, or however you want to do it. Just take those equations that we put up there, grab those. The z components for r and the z component for f will be 0. So we just plug those in. Some will be a little simpler there. When we get done doing that cross product, those zeros will pop out. And the nice thing is note which direction is that. It's negative, but it's giving me direction here in terms of k. Remember, k is going to be that perpendicular distance that we've been doing in and out of the board that the physics majors don't like. But the nice thing about the cross product is it gives me the correct sense, and it also gives me the correct direction. Okay, long lecture.